Okay, so today we're going to be talking about redox reactions. So some common examples of redox reactions is photosynthesis and respiration. So respiration is the oxidation of certain fuel sources. So examples could include sugars, fats, or just your simple carbon compounds such as methane. Displacement reactions, which we'll be doing in the lab, and your classical kind of oxidation, which is your rust of iron. So we can all see that quite commonly around the Gold Coast because we're so close to the beach. So what are redox reactions? So redox reactions are the full or partial transfer of one or more electron. So examples, and a particular example that we could look at is sodium chloride formation. So sodium solid is fairly toxic. Chlorine gas, as you probably are aware of, is quite toxic, but together when they have a redox reaction they make sodium chloride, which is your edible table salt. So another example is the oxidation of methane. So we've got CH4 being oxidized with O2. So oxygens are adding to that carbon and displacing the hydrogens, and we make water as a byproduct, and carbon dioxide, which is the oxidized state of the methane. So you can see that in this oxidation reaction we've added oxygens to the carbon, so we've removed the hydrogens and added oxygens in the place of those hydrogens, and that's a classical example of visually looking at a compound and seeing if oxidations occurred. So we can look at a compound and see if there's oxygens added or more bonds to oxygens added, then it's becoming more oxidized, and in this process we're losing hydrogens. Okay, so less hydrogens, more oxygens is oxidation, and the opposite is what we call reduction. So reduction is when we're losing oxygens and we're gaining hydrogens. Okay, so what actually happens is the transfer of these electrons, and the way that so electrons that are lost by one species is gained by another species. We don't just have electrons floating around, they're actually being transferred. So we need to make sure that the oxidation reaction electron transfer is equal to the electrons gained by the redox reaction or the reduction. So oxidation, reduction. Oxidation involves the loss of electrons, and reduction is the gain of electrons. So personally I remember that by OIL, 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 rig, RIG. So oxidation is lost, OIL, reduction is gain, RIG. So oil rig, oxidation is loss, reduction is gain. And when we talk about this oil rig, we're talking about electrons. So what's happening to our electrons? So here's a table of common oxidizing and reducing agents. So if something is being oxidized, it's acting as a reducing agent, and if something's being reduced, it's acting as an oxidizing agent. So by being reduced, the other species that it's close by to is being oxidized. So it's an oxidizing agent. So it's the opposite to what's happening to itself. It's making that happen to the other species that's close by. So examples of oxidizing agents are O2 gas, okay, your halogens. So oxygen gas goes to O2 minus, your halogens goes to Cl minus or Br minus. You've got your protons, so H plus going to H2, okay, and you've got your nitrate ions, NO3 minus going to NO or NO2. So these are oxidizing agents, so the actual process of those are a reduction process. So reducing agents, so we've got H2 gas going to the proton, so you can see it's going back the other way there. So reducing agents is when the H2 gas is being oxidized into H plus. Okay, so oxidation is loss. We've got the loss of electrons in that particular process. We've got our reactive metals, okay, so sodium and potassium. We've got carbon going to carbon dioxide, and we've got carbon monoxide going to carbon dioxide. So you can see carbon going to carbon dioxide is kind of like 2 steps of oxidation, whereas carbon monoxide going to carbon dioxide is 1 step of oxidation. So reducing agents are being oxidized because they're making the other species being reduced. And some of these examples we'll be doing in our lab. So how do you know by looking at a particular reaction what's being oxidized and what's being reduced? So what we do is we count up our oxidation numbers for a particular element that's in a compound. So it's a way of keeping track of the electrons in redox reactions. So oxidation numbers come about because electrons in a covalent bond are not equally shared between the two atoms. So if you have an electronegative atom, it means that the electrons will be most likely spending more time on that particular atom. So for example, if you look at this water here, we've got oxygen and we've got hydrogen. So oxygen and hydrogen have 2 electrons in this particular bond here. Most of the time, the oxygen has the electrons from that bond sitting on top of the oxygen or close to that oxygen because it's more electronegative. It's drawing those electrons or attracting those electrons to itself. This means that you can count those 2 electrons as being on oxygen, and then hydrogen would be electron deficient. Okay, so oxygen would be a 2- because it's got 2 extra electrons, and hydrogen would be a +1 because it's lost that electron that it usually should have. Okay, so by looking at the polarity of the bond, looking at which species is more likely to be attracting the electrons onto itself, we can count those electrons, and it's called oxidation numbers. So the rules for assigning oxidation numbers are quite straightforward. So if you have a free element, its oxidation state for each atom is 0. So free elements are elements that are in their elemental state. So when it's only that element. So iron solid, oxygen gas, hydrogen gas, and so forth. So you can see these elements have no charge on them, and they're just by themselves. So if that's the case, then it's 0. If you have a monoatomic ion, then the oxidation number is given by the charge on the ion. So if you have chlorine with a negative charge on it, it's a -1. If you have iron with a 2+, it's a +2. If it has a 3+, then it's now a +3. So if you have an atom that's by itself with a charge, the oxidation number is the charge on that particular element. So certain elements always have the same oxidation state. So your alkali metals, so your first column in your periodic table, your alkali metals, so lithium, sodium, potassium, they're always +1. Your alkali earth metals are the next column over, so magnesium, calcium, strontium, barium, they're always +2. Okay? The other one is hydrogen is always +1. There is one exception with metal hydride compounds such as lithium hydride, but we won't be talking about that one. The other one is oxygen is always -2, and that's because oxygen is so electronegative it keeps the electrons on itself. And the exception for that is your peroxides such as H2O2. Again, we won't be looking at that example. So halogens, F-, Cl-, Br-, I- are usually -1. So how do we work out the oxidation state of a particular atom within a compound? So oxygens and hydrogens are always -2 for oxygen, hydrogen is always +1. So if you look at a particular compound, you're not looking at oxygen and hydrogen, you're looking at the other one that's left over. So this one we've got CH2O. We know what oxygen always is, we know what hydrogen always is, so the one that we don't know is carbon. So we want to work out the oxidation number of that carbon. So it's just algebra, so you can write it as a formula. So overall this compound has a 0 charge. So we go X plus 2 minus 2 equals 0. So plus 2 because we've got 2 +1s, so hydrogen is always +1. And this is -2 because we have 1 oxygen and it's always -2. And algebraically you just solve for the unknown. So carbon in this case, we've got +2 minus 2 gives me 0, and it's 0 overall, so carbon must be 0 overall. Okay, now we've got methanol. Okay, so again, carbons and hydrogens and oxygens. The oxygens and hydrogens, we always know what that is, so we're trying to work out what carbon is. So oxygen's -2. Overall we have a 0. So we've got -2, and then we've got +4 from these hydrogens. So we've got -2 plus 4. We've got 0 overall. So therefore our carbon must be -2. Okay, now, so the sum of the oxidation states of the ions is equal to the charge on the ion. So if you have a complex that's not neutral, so no charge on it, and it has an overall charge, then you just have to do the same thing but give that charge overall. So what do I mean? Let's look at CH3, CH2O-. So overall we have a negative charge. Our oxygen we know is -2. We have one of them, so we've got -2. Our hydrogens are +1, and we've got 5, so we've got +1. So +5 -2 gives us +3 equals -1. And then we've got 2 unknowns. So we've got 2x plus 3 equals -1. So therefore our 2x's should equal -4. So each x equals -2. Okay, so let's have a go at these examples here. So we've got Mn in Mn2O7, we've got S in H2SO4, O in O2, and B in BrO3. So if you want to pause the video now, you can have a go at doing these, and then I'll go through them. Okay, so let's go through these. So Mn in MnO2. So we want to assign the oxidation number of manganese in manganese Mn2O7. So now we have 7 O2s, so we've got 7 times -2, okay, so we've got -14, and overall this equals 0. So we've got 2x plus -14 equals 0. So rearranging that, we have 2x equals 14, so x must equal 7. So with the next one, we have sulfur that we're trying to work out. So we've got H2SO4. So putting in our values, we know we've got 2 hydrogens, which are +1. We have our unknown sulfur, and then we have 4 -2 for each oxygens. So overall, that gives us a 0 because there's no charge on this particular molecule. So we've got +2 plus x minus a gives us 0. So rearranging that, we get x equals +6. Okay, so now looking at 3, we've got oxygen in O2. So O2 is in its elemental form, so therefore oxygen must be 0. So that's our first rule. And now we've got bromine in BrO3-. Practice problem we'll go through in the lecture, and I'll put up some resources for you to follow through on a similar type of problem. So this one here is using our standard reduction potentials table, and this is done at standard room temperature, which is 298 degrees Kelvin. They're 1 molar solutions, and they're done at 1 atmosphere. So what they've done is they've listed the half reactions according to their potential to their potential, so their E0 value with the reduction equations. So at the top are the half reactions that have the highest reduction potential, and at the bottom they have the ones that have the lowest reduction potential. So the guys at the top, they're more likely to reduce, and the ones at the bottom are more likely to be oxidized. So because the ones at the top are the strongest reducing reactions, they are strong oxidizing agents because they're being reduced, the other guys being oxidized, so they're oxidizing reagents. Okay, so remember, an E0 value that is negative, it's more likely to release electrons, and if it's positive value, then it's more likely to accept electrons. Okay, so when we're trying to predict reactivity, which you will be doing in your laboratory, you need to have a diagonal relationship between the species in question to see if a positive reaction will occur. So if there's a downwards diagonal relationship, like for example Fe3 plus and copper solid, then there will be a reaction taking place. If there's any kind of other relationship, then there won't be. So if it's upwards and diagonal, there won't be. If it's on the same line, then it won't be. So what do I mean here? We've got Fe3 plus reacting with copper solid. Okay, so the reason for this relationship is because we'll get an E0 of the cell being positive, so it means it's spontaneous. So we're going to learn more about this equation at a later date in the next subject, but for now you just need to know that the downwards diagonal relationship means that a reaction will occur. So pretty much it means that the cathode minus the anode would be positive. So the reduction minus the oxidation here. So don't worry too much about the equation for now. What we're looking for is that downwards diagonal relationship. So Fe3 plus and Ag solid will not have a reaction. Fe3 plus and MnO2 will have a reaction. So we're looking for something on the left hand side reacting with something on the right hand side that's in a downwards diagonal relationship. Okay, so let's look at the metabolism of glucose versus fat for energy via oxidation. So in our bodies we have the metabolism of fats and glucose, and they're being oxidized, and part of this process of metabolism is producing these coenzymes and enzyme coenzymes. Okay, NADH is an example of a coenzyme. So a coenzyme is a substance that enhances or is necessary for an action of an enzyme. So they work with the enzyme for the enzyme to do its job. They're electron carriers, so they carry electron pairs in their reduced form. So NADH and FADH2 are electron carriers, so they carry electrons around and then they drop off the electrons where they're needed. So producing these electron carriers is a product of metabolism, and then they go on to do what they need to do with them. So if you look here, we've got our fatty acids, okay, and we have beta oxidation, and we produce one NADH unit, and then it goes to acetyl-CoA, and then it goes into the citric acid cycle, making that carbon dioxide, and we're producing electrons that go into the oxidative phosphorylation, and we get ATP being produced. So we have a similar thing when we have our glucose 6-phosphate. So this is the structure of glucose 6-phosphate, and this is the structure of our fatty acids. So you'll see fatty acids have a hydrophobic tail. Okay, so the hydrophobic tail wants to be in an anhydrous environment, which we've talked about before, and we have that hydrophilic head. So these fatty acids can stack really well together because like dissolves like, or like likes to be with like, so they stack up really nicely, and you can get a quite dense population of these fatty acid molecules packed entirely together. Carbohydrates, on the other hand, are very polar, so they like to be in polar environments. So carbohydrates exist in a hydrated state. So you've got a 1:2 ratio of carbohydrate to water. Okay, so the water coordinates highly with your carbohydrates, and this means that it's got less carbohydrate per mass because you've got this water molecule that's taken into account as well. So you get less energy from carbohydrates because there's less carbohydrates there per gram because you've got your water molecules compared to fat. Okay, so fat doesn't have that water interfering, you get more energy per gram of fat, and that's because it's able to pack in nice and tight. So let's have a look at how we can work out this energy just simply looking at the oxidation series for these types of compounds. So if we look at fatty acids, so when fatty acids are oxidized, we get carbon dioxide and water and energy being produced. So if we know this is our fatty acid formula, we can balance this equation and we can see that we get 18 CO2s and 30 waters. If we compare that to carbohydrates, when we balance it, we get 6 carbon dioxide and 6 water. Okay, so you can see there's a lot more produced from one fatty acid than what we get from a carbohydrate. Another way of looking at it is looking at the carbohydrate series. So if we look at methane, we know each hydrogen is a +4, so carbons are -4 at this stage. Here we've got -2, +3, 4, -2, +4 gives us a +2, so the carbon must be a -2. The next one we've got +2, -2, so the carbon must be a 0. The next one we've got -4, +2, so the carbon must be a +2. And the last one, CO2, we've got -2 times 2 gives us -4, so the carbon must be +4. Okay, so we've got our oxidation series there, and you can see we're going from a -4 all the way up to a +4 at the most oxidized. So if you count up those electrons, going from an alkane to a carbon dioxide, we've got 8 electrons. Going from an alcohol, which is what we have on each of the carbons on a carbohydrate, we're only producing 6 electrons. So there's less electrons being produced per oxidation. So that's another reason why fatty acids give more energy than carbohydrates, because there's more electrons that can be carried around and put into your electron transport chain. So talking about electron transport chain here, we have our oxidized form and our reduced form. So we have O2 going to H2O. Okay, so when O2 goes to H2O, it's becoming more reduced and we're losing electrons. So we're transferring electrons down the chain. So what we have here is our E0 values. Okay, so we've got the highest one up here. We've got a downwards and diagonal relationship occurring. And these are all the states in which the molecules exist in the electron transport chain. And finally we have NADH, which is the most reduced form, and that one is where we end up with. Okay, so we can see here we have NADH going to NAD. We're dropping off those electrons into the chain. We have our cascade of events that are occurring. Okay, so we've got our 4 protons being produced, pumped into the inner membrane, and then we have our Q, which is our ubiquinol being formed here. So you can see this is the oxidized ubiquinol, and this is the semi-quinone product. So this is the half reduced, and this is the fully reduced. So you can see that this oxidized species here has 2 carbonyls, whereas the next one we only have 1 carbonyl and 1 alcohol, and then the fully reduced form, which is ubiquinol instead of ubiquinone, indicating that it's an alcohol instead of a ketone, has 2 OHs on it. Okay, so this is what's actually happening in here. And then we get our cytochrome C, okay, and then we have more protons being produced, so we have like a really high concentration of protons in the membrane. And then what actually happens at the end is we have a proton pump. So we have the protons coming out, and we have this ADP to ATP reaction occurring, and this is where our energy is being produced. Okay, so the ATP synthesis is driven by a proton motive force, and it's got to do with the electrical potential inside and outside of that membrane. Okay, so now we have complexation reactions. Okay, so this is just for interest's sake, and we'll be talking about this more so in biological and physical chemistry. So it's involved with complex ions. So you have a charged species made up of a metal surrounded by its ligands. So the ligands are Lewis bases. Okay, so they have a lone pair of electrons that donate into the empty d orbitals of the metal, and the number of electrons that a metal can hold is what we call a coordination number. So each metal has a typical coordination number, so it might have a 4 or a 6 or a 2 coordination number, and that means that it can hold that many ligand pairs being donated, so ligand electron pairs being donated into the metal. Okay, and this is involved in dissolving insoluble compounds. We can use a weak base to pull it into solution. So if we look at AgCl solid going to Ag plus and Cl minus, we've got an equilibrium here, and it's to pull it to the right. Cl is a very weak base, and it's hard to remove it from solution to drive the equilibrium into the right. Instead of removing silver from the solution by forming complexes with a ligand, we can complex the silver because it's a metal, and we can drive it into making that Cl minus and dissolving that AgCl. So a potential ligand that you could use would be the NH3 ligand, and we could form an AgNH3 2+ complex. Okay. We can get different types of ligands, so we can get a monodentate where we have 2 electrons, so an electron pair being donated to the ligand. Okay, so we can see water is a monodentate ligand donating a lone pair into the central metal, okay, which in this case is aluminium. You can get bidentate, which is like the oxalate anion, so it has 2, so this is the one molecule, and it has 2 oxygens that are donating into the chromate in the middle. So this brings you into your hemoglobin example. So you've got the small part of a protein molecule, which is your globin, and it has a nitrogen on the end, which has the lone pair, and it donates into the iron. And then you have your heme porphyrin ring, which has 4 nitrogens in it, and then you have the water molecule that donates in. Okay, so we have 1, 2, 3, 4, 5, 6 groups donating in, and the water molecule can be replaced by oxygen depending on whereabouts the hemoglobin is and how it needs to act. Okay, so this is what we call a heme or a quadradentate ring structure, and we've got the hexadentate, which is when you have 6 ligands, and that's the EDTA. So depending on the environment, EDTA can act as a 4 or a 6 coordinate ligand. So this kind of brings into your chelation therapy. So this is when a patient might have excess heavy metals in the body. You can use chelation therapy, which is where you have a chelating agent that is ingested and it coordinates to the metal, and then it's removed, it's excreted and removes that metal ion. So for example, patients that suffer from high iron, so hemochromatosis, may need a chelating agent to coordinate to the metal, the iron, and pass it out. So here's one here. Okay, so we've got a tridentate ligand, so one of the alcohols, one of the nitrogens, and another alcohol here will coordinate to the central ligand. Okay, and then you'll have that 2 of them coordinating to a ligand, to a metal and passing. Okay, so that one was approved by the FDA in 2005 for use. Okay, so these are the support materials for this topic, and there's lots of resources online for you, so please make sure you